So hello everyone. Today we are presenting our final project titled Predicting Pokemon Types Using Image Classification. I'm Prashtay and I'm joined by my teammates Dasha and Shivsundar. Together we have explored how deep learning, particularly CNNs, can be used to classify Pokemon based on their primary and secondary types. So Pokemons are designed with visual patterns that often align with their elemental types, like flame patterns for fire types and aquatic features for water types. With the rise of image based deep learning models, we aim to automate the classification of Pokemon types using our visual data. This is applications in automated categorization, that is AI driven character classification and game development, and even fan based research to analyze trends in Pokemon designs across generations. So, additionally, we have aimed to explore evolution based prediction, studying the relationship between pre evolved and evolved Pokemon to see if visual features evolve consistently with type transition. So, we've used the Pokemon image dataset from Kaggle. It covers generation 1 through 7 and includes high quality sprite images and corresponding type labels. Some Pokemon have dual types, making this a multi labeled classification problem initially, but for this project we focused on single label classification, that is only type 1. So our pre-processing pipeline included resizing all the images into 128 by 128 pixels and normalizing the pixel values to 0 1 range, and later applying data augmentation techniques like rotation, horizontal flipping, and brightness adjustment to improve our model generalization. So for training, we performed five-fold stratified class validation using a 80-20 train validation split. Each fold to ensure balanced sampling for classes. So we selected the top four most frequent Pokemon types to reduce class imbalance. So we resized the image into 224 by 224 and passed through a transformation pipeline that involved all the horizontal flipping, random rotation, color jitter, image net normalization. So we used ResNet 18 later and a deep residual CNN pre-trained on ImageNet and replaced the final fully corrected layer for for four class classification. So training configuration had a batch size of 32, 6 epochs, and GPU enabled training. And we've covered evolution matrix as accuracy, precision, recall, FN score. We've also kept a confusion matrix and results reported as mean standard deviation across folds. So baseline model was a random forest classifier trained on flattened pixel values. It achieved limited performance, that is only 51.2 accuracy, due to its inability to capture spatial structures and images. We transitioned to Resonate 18 later, a CNN architecture that uses residual block to prevent vanishing gradients. This model was fine-tuned into two stages, that is stage 1 for training only the classification head, freezing the rest of the layers. And stage 2 was end-to-end fine-tuning, allowing the model to adapt to Pokemon-specific visual patterns. The best recorded accuracy was around 78.98, showing significant performance gain over the transitional models. The Resonate 18 model showed consistent improvement over all folds in terms of accuracy and micro average reference score. The confusion matrix helped identify frequent misclassification, and overall results indicate the model's effectiveness in learning discriminative visual cues tied to type classification. These are the outputs, the predicted values versus the true predictions. So takeaways, Resonate 18 provided a efficient and balanced solution. So it's relatively lightweight architecture which helped avoid overfitting while still capturing complex features like elemental color tones and body shapes and textures. So pre-trained ImageNet weights enabled faster convergence and better generalization to Pokemon's diverse art styles. So that makes Resonate 18 a strong baseline for further exploration such as multi-label classification with dual types, etc. So our project workflow followed a clear four-stage pipeline, that is data pre-processing, that is label encoding, resizing, normalization, and augmentation. Then model development, that is, we started with a baseline model, that is random forest, followed by a deep learning resonant 18 model. Evaluation using fold-wise metrics and performance visualization, and then documenting the findings and communicating insights to slides and reports. So we credited data sets and key research papers that guided our project, that is including EfficientNet, which was evaluated during exploration, and Kaggle's Pokemon dataset. These informed our model's choice and augmentation techniques. So yeah, thanks for listening. We are happy to take any questions about our methodology, model architecture, or evaluation metrics. Thank you.